Okay, everybody, so here we are. This will be part 3 and probably the final part of my improper integrals video series. Okay, so I still think we've only done case 1 of an integral is improper if, okay, I don't think we've looked at case 2 yet, but I've made so many videos today between my classes, it's all a blur at this point. But nonetheless, I know that I still need to cover the problems in this video, even if I can't remember exactly what was in the videos that I made earlier today. Anyway, so how about this? Let's do this one to start with, okay? Now notice, in this integral that I'm looking at here, okay, lower limit of integration is 2, upper limit is 11, then infinity is not one of the bounds of integration. Okay, so it's not that kind of improper integral. There is another kind though. If one of the bounds of integration was correlated or associated with a vertical asymptote on that function, then that's also an improper integral. Okay, so if I say, well, the function's 1 over x minus 1, and my bounds are 1 to 4, okay, then there is a vertical asymptote, as a matter of fact, on this curve at x is equal to 1. And then here's what roughly that curve looks like. All right, so what about that would make the integral improper? Well, with the integrals where infinity was one of the bounds of integration, that made the region on the graph unbounded, okay? Infinite in its span, in other words. And that's my very first video on this. I started by just getting you acquainted with that concept, all right? So if one of these bounds was associated with a vertical asymptote on that function, then there you go. It's another type of improper integral. Okay, now, so most of the ones I'll look at in this video are of that kind. Now, let's see, here's the first one I want to look at. All right, so I have my integral from 2 to 11, 1 over root x minus 2. And as a matter of fact, that function has a vertical asymptote at 2. And if I sketch the graph and plot points and so on, it's going to look like this. The reason I know that there's a vertical asymptote at 2 is just by definition of what a vertical asymptote is. If in that function x approaches 2 from the right, you'll find that y goes to infinity. So that curve climbs up very steeply there on that vertical line x is equal to 2. So when I see this integral and I see that function, the 2 is the number I notice. And there's a vertical asymptote there. Another cue that can tell you that's what's happening is that this function is defined at 11. I can put 11 in, no problem, but it's undefined at 2. All right, so that's another way that you can know that something's not right with that 2 being there. Okay, now, here's how we do this. The 2 is unsuitable for calculation there. You can't plug in the 2, all right? The number 2 is not in the domain of that function. There's a vertical asymptote. There's lots of ways to say this. So that 2 we need to replace. It's kind of like when I said earlier, well, if infinity was a bound of my integral, infinity is not a number that I can do calculations with. And so here I'm seeing that the 2 is like that, all right? So here's what we do. We do limit, and I replace the 2, the number where there is a vertical asymptote, with b, which is a number that's under my control. And I leave the 11 because there's no issues with the 11, okay? And otherwise, I'm going to leave this function in there the way it is. Okay, so root x minus 2, okay. But I want the b to do what? Think about it like this. I'm trying to measure all this area. I can't really measure from 2 to 11 because there's nothing at the 2. You know, the 2 is not in the domain. There's nothing there. But suppose you still wanted to measure all this. You could get a pretty good idea of how much area was here if you measured the integral from 2.1 to 11 or 2.01 to 11. You get the idea? Take a number just slightly to the right of 2 and measure the area from there to 11. All right, so here's what we want to do with the 2. We want to replace with b, and we want to have the limit as b goes to 2 from the right. Why not from the left? Well, we're not looking over here. That's why. That's one reason. Okay. So, all right, there's the story. Now, if you replace the lower limit of integration, if that's the number where there's a vertical asymptote, you're going to replace it with b, and then b is going to go to that number from the right every single time. That's always how it's going to work, but I explained why that is. Okay, it's like you're saying, I can't really measure from 2 to 11, but I could measure from like 2.1 to 11 or 2.01 to 11 or something like that. Okay, now what do you think happens next? Well, you find the antiderivative and you evaluate with the bounds, but ultimately when you do that, at some point you're going to say, I got to take the limit as b goes to 2 from the right. Okay, so let's see, the antiderivative of this is 2 root x minus 2. So in this video, so far this semester we've done lots, I made lots of videos over forms of integration. I probably post like 4 videos just on u substitution alone. And so I think at this point I'm probably not going to focus so much on the integral, the working of the integral. The finding of the antiderivative in the video, but that's something that you can ask me about if you need to. All right, so there we go. So I got like that, and then I'm going to do there. That's the antiderivative. Okay, it is just a matter of u substitution. Truth is, and then I put 11 in. So what do you get when you put 11 in? 11 minus 2, that's 9. So root 9 is 3. So I'll get 6, and then I'll get 2 root x minus, so not x, b. I put b in for the x. Like that, and I want b to go to 2 from the right. Okay, now of this thing right here, what happens if that number goes to 2 from the right? What's like 2.0000001 minus 2? It's practically 0, okay? So if b goes to 2 from the right, you'll find that entire component of this expression is going to go to 0. All right, so my answer, so it's just 6. It's 6 minus 0. What's the term for that? Well, when we work an improper integral and the answer is finite, we say it converges. Another way to think about that is that the physical area here, even though there's no ceiling on it, even though that's unbounded up there and there's really has an infinite vertical span to it, its area is finite. It's 6 square units. It's the same size as a 1/6 rectangle on an equivalent scale. All right? Okay, so that's one way that we handle improper integrals that deal with vertical asymptotes. Let's look at another one. All right? What do you think about this one? So it says integral from 0 to pi over 2 secant squared x dx. Okay? And the graph secant squared has a vertical asymptote at pi over 2. And so how do I know that? Well, all right, I could plot some points if I wanted to and see the overall pattern of the points, and that's what the graph is anyway. But I could see secant squared is 1 over cosine squared. And the cosine function goes to 0 as x goes to pi over 2 from the left. Cosine of 90 degrees is 0. And the closer that angle is to 90 degrees, from underneath, like 89.9, 89.99, then the closer the cosine is to 0. That's why there's a vertical asymptote at pi over 2. So in this function, it's like as you go to pi over 2 from the left, you're dividing by close numbers that are smaller and smaller and closer to 0, yielding an overall larger and larger answer when you divide. Okay, So let it be known that yes, there is a vertical asymptote at pi over 2. So here's what I need to do. I was measuring, trying to measure all this. How do you think you can measure the area from 0 to pi over 2? Like pi over 2 is about 1.57 or so. I could go from 0 to 1.4, 0 to 1.49 or something like that. I can go right up to that red line, that asymptote, but not quite get there because there's nothing at the asymptote. So I go right up as close as I can to it. So here's what I'm saying. The way we need to rephrase this is we'll leave the 0 alone. There's no asymptote at 0. There's a point, 0 for x, 1 for y. But we'll replace that pi over 2, that number that is unsuitable for calculation and secant squared, where there's a vertical asymptote. We'll replace that with b, and we want the limit as b goes to pi over 2. What do you think, from the left or from the right? How are we going to capture this area? We want to go from here towards as close as we can get to that asymptote. So we want to go from b goes to pi over 2 from the left. All right. Why not from the right? Well, we're not looking over there. That's another reason why we don't do from the right. So, okay, so that's the thinking behind why it says b goes to pi over 2 from the left. Another way to think about it is if that upper limit of integration is where the vertical asymptote is, then that limit will be from the left, all right, every single time. So, okay, so I got secant squared x dx. Now, this is a pretty easy integral to do because I know that the derivative of tangent is secant squared, so I want to do the limit as b goes to pi over 2 from the left. All right, antiderivative is tangent. And I look at it from 0 to b. So what I'll be doing this time is figuring out, however I can, limit b goes to pi over 2 from the left, tangent b minus tangent 0. Okay? All right. So think about it. What happens to tangent of b if b goes to pi over 2 from the left? Now, in one of the other videos I did, where was it? I tried to get you to have kind of a sophisticated understanding about this, that just, you take tangent of an angle and you get a number, and say tangent of an angle is, if you were to draw the angle this way, is going to be that y side over the x side. And I said, well, try to think about what happened if you could imagine I push this angle closer to 90 degrees, like I could physically push it, and this triangle is going to morph. How's the triangle going to morph? The x side is going to become much smaller, and the y side will become much bigger by comparison. And if tangent is y over x, y getting bigger, x going to 0, that's going to cause tangent of the angle to go to infinity. So the closer that angle pushes to 90, the larger the tangent of the angle gets. It goes to infinity, all right? So I wanted you to have that kind of sophisticated understanding about it, but we also did it on calculator. We could say, all right, what happens if I make that b there, that number, closer to pi over 2 from below? Well, my calculator happens to be in degrees, so I could do like a tangent of, 89. Let's see what I get, 57, okay. And then tangent of 89.9, that's a little bit closer to 90 from underneath, and I get 572. Let's go a little closer, one more. Tangent 89.999 and 57,000. Yeah, it does appear that every time I make that angle a little bit closer to 90 degrees from below, the tangent just gets bigger, okay? So this one will be infinity minus 0, or just infinity, okay? This integral will diverge. That's what we'll say about it, all right? The integral diverges, the improper integral diverges. Now, as you look at these problems, there's several things that I want you to think about. And it's one, when you're presented with the integral, do you have like a rough understanding of the graph and which of the numbers there's going to be a vertical asymptote at? First thing to understand. Second thing, do you see how the limit comes into play? I can't really measure the area from 0 to pi over 2 because there's nothing at pi over 2. The curve climbs to infinity there, but it never gets to pi over 2. So I can't really go from 0 to pi over 2. I can go from 0 to somewhere and make that somewhere, push as close to pi over 2 from the left, from this side as I can in order to cover this whole region. But, that's why that limit is involved, and that's why it is the way it is. Third thing, once you find the antiderivative, you put the numbers in, somehow you're going to have to do that limit, all right? And, limits, that's something that you learn about in Calculus 1. All right, let's establish that you probably have seen it before. Nonetheless, you might need a little bit of review on it, and, you can ask me about that if that's something that would be called for. All right, but I am saying a little bit about the limits as we go along. Okay, let's do another problem. So let's try this one. Okay, so this one has a totally different wording than the others up to this point. It says calculate the arc length of that curve over the interval from x is 0 over to x is 5. Okay, so I drew like a little sample segment of that curve, and it looks something like this. As you go from 0 to 5, well, when x is 0, there's this point on that curve where y is 5. And then when x is 5, there's this point on that curve where y is 0. Okay? And when we say calculate the arc length, we say, well, can you measure the actual length or distance from this point to that point? Can you measure the length of that part of the curve? So arc length is something that I covered in an earlier video. And the formula that I gave is this. It's going to be the definite integral from 0 to 5. 0 to 5 are the bounds for my x that trace this portion of the curve. Root 1 plus y prime squared dx. All right, so our task then is to evaluate that integral. So let's do this. Let's find the components that we need. So first of all, y prime. What's the derivative of root? How about, I don't want to waste space down here. Take that back. All right, so what is y prime, if that's y? All right, so y prime, if I use the chain rule, that's going to be negative root 25 minus x squared. Okay, that's with the chain rule. So there's y prime, so I would need to do 1 plus y prime squared, all right? So here goes. I'm going to have my integral from 0 to 5 root, all right, 1 plus, and then there's my y prime. Imagine if I squared that. It would no longer be negative if I squared it, and I would get x squared over 25 minus x squared, okay? So I'm going to get x squared over 25 minus x squared. So there's my integral. Now that one is probably going to take some work in order to answer it. So what I'd like to do is I would like to add these together, okay? Like suppose like I want to say, how do you add 1 plus x squared over 25 minus x squared? I get a common denominator of 25 minus x squared. And 1 is 25 minus x squared over 25 minus x squared. That's how you put 1 in terms compatible to add with that. And so here's what that's going to look like. It's 25 minus x squared plus x squared all over 25 minus x squared. That's what you get if you add those two fractions. And so I'm going to get 0 to 5 root, let's see, what did I say? 25 on top. And then underneath it, also under the root, 25 minus x squared dx. Okay. All right. Now, let's go one more step further. Square roots distribute over division and multiplication, but not over addition and subtraction. So I could look at this as root 25 over root 25 minus x squared. So let's say this. Let's say 0 to 5, 5 being root 25, over root 25 minus x squared. Okay. Now, when we get here, this is something that you could do by trig substitution, all right? But it's fine with me at this point, since hopefully we learned the trig substitution, we practiced it, that I could give you some formulas. So let's say here's a formula. Remember, I made this video over tables of integrals, and where we can look up the answers to some common forms of integration. But let's say here's one that you might find. Okay, so 1 over root a squared minus u squared, use the variable. And that one is going to turn out to be inverse sine u over a plus c. Okay, so that's what we're looking at right here. All right, if you factor out the 5. Okay, so that's the first thing, is that I think I know the form of integration I need. It's right here. So I'm going to put this aside. Another thing is this an improper integral? Okay. One of these numbers, if you just take that at face value, is going to give you a vertical asymptote on that. I mean, look at it like this. If can x be 0 in this function? Yeah, I say put 0 in. 0 squared is 0. 25 minus 0 is 25. Root 25. Yeah, you can calculate all that. What about 5? Okay, 5 squared is 25. 25 minus 25 is 0. So yeah, if the x was really close to 5 from below, that would be an extremely small number close to 0. And when you divide by numbers that are very small and very close to 0, you get very big answers. So I want to say about that 5, I notice that we have a vertical asymptote. I'll just put vertical a. That's the number that's not suitable for calculation. So this is an improper integral. That right there, that's an improper integral for that reason. I'm not saying that there's a vertical asymptote here. I'm just saying once you set up the integral to measure what you want to measure, which is the arc length, then the function that ends up being right in front of you has a vertical asymptote at that upper limit of integration. Okay, so that's the situation we're in. So here's what we need to do. Here's how we evaluate improper integrals. I want to do the integral from 0 to b, and I want to have b go to 5 from below. Okay? And then I'll get 5 over root 25 minus x squared. Okay, that's how I'm going to do it. Now I have my answer for this one. If I factor out that 5 right there, then I have the antiderivative 1 over root 5 squared minus x squared. Here the variable is u, there the variable is x, and they make a direct comparison to each other otherwise. So let's do this. Limit b goes to 5 from the left. And then here's that antiderivative from that formula I just showed you. We're going to factor out that 5, and it's going to be here. Otherwise, we're going to get the inverse sine function of x over 5 from 0 to b. Okay? All right, so let's see if we can do this then. All right, so we'll put b and we'll put 0, then we'll find a way to do the limit. So limit b goes to 5 from below, 5 sine inverse b over 5 minus 5 sine inverse of 0. Now, suppose b goes to 5 from below. Now, I have to make a quick comparison to a problem that I just did. Here, if, say I wanted to do this limit b goes to pi over 2 from below, I made my case to you that it was infinity. Why couldn't I just do this? Let's see. I'll plug tangent, and my calculator happens to be in degrees at the moment, so let me just put pi over 2 in. I'll just plug it in and see if I can get the answer that way. All right? So I put 90 in, all right? Or I could put my calculator in radians and put pi over 2 in. But maybe you're wondering, can I do that limit just by plugging the number in? And it doesn't work. I mean, you just don't get an answer, all right? It doesn't tell you anything that's useful. All right, so sometimes we really need to know how to do limits in order to get our calculations right. Here, though, I don't think that that's a problem, right? If I said b goes to 5 from below, well, what if I just put 5 in? Do I get an answer? All right. If I do, then I think that will tell me what happens as b gets closer and closer and closer to 5 from below. So if I put 5 in for b, 5 over 5 is going to be 1. And do you know an angle that has a sine of 1? It's pi over 2. Or you could do this. You could say, what sine inverse of 1? And it's going to tell me 90 degrees because, in fact, sine of 90 degrees is 1. So this limit here, all right, if b goes to 5 from below, like 5 right there, that's going to be sine inverse of 1. So that's going to be 5 times pi over 2. Okay? All right, and sine inverse of 0 is, in fact, 0. So let's put this as 5 pi over 2. Our improper integral, converges to 5 pi over 2. All right, the way I did the limit was a little bit different in this problem compared to some of the others. But like I said, if the limits are the part holding you back, then we'll talk more about the limits. All you have to do is ask. Okay, so I had one more on my list to show you. Oh, what's that mean? That's the length of this curve right here. It's 5 pi over 2 units of length. All right, so I had one more that I wanted to show you. All right, and it was this one. And I made a really terrible drawing when I did this, but I'm just exhausted. I've made so many videos today between the classes. I didn't do a real good job drawing that picture, but maybe you can forgive me. But let's say that the question goes something like this. A picture is given, and we get an equation for the curve in the picture, and I've done some shading, and it says calculate the total area that's drawn below. So you would think of this as the total area between the curve and the x-axis. All right? This curve has a horizontal asymptote on the x-axis, meaning it closes in on the x-axis closer and closer, but this little bit of space on each end between the curve and the x-axis never disappears. There's always a little bit there, all right? And I told you my drawing was not that good, but in spite of the appearance of my picture, this curve is symmetric with respect to the y-axis. What does it mean to be symmetric with respect to the y-axis? It means that this part of the graph on the left-hand side of the y-axis is a mirror image of that part of the graph on the right-hand side of the y-axis. How do you know that? Well, because by nature of this formula, whether I put a positive number in for x or the same or the opposite negative number, like if I were to put 5 in for x versus negative 5, I will get exactly the same y. The reason for that? Well, you're going to take the x and square it. So whether you put 5 in or negative 5, 10 or negative 10, you're going to get the same y. That's why it's symmetric about the y-axis, all right? So here's how we could do it. We could find the area there in two ways. So my total area could be thought of like this. The integral from negative infinity to infinity. Because this curve, having a horizontal asymptote on the x-axis, does span forever in each direction. To get all that area would be from negative infinity to infinity. Okay, so we could do like that. I don't know. I mean, I think if you saw a problem like this in a book or something, that's probably how it would be set up, all right? But I guess, like, I do take issue with that a little bit because the problems we've done so far, I said, well, an integral is improper if one of the limits is infinity or negative infinity. And I've showed you how you handle that with some examples. But what if they're both infinity? I mean, each one of them is supposed to be a limit. So I don't know that I like having two infinities right there. I guess we could break the problem into two parts and like go negative infinity to say 0, and that'd be one problem, and then add together with 0 to infinity, and that'd be another problem, and work them both and add them together. But how about this? Let's take advantage of the symmetry. Isn't the area of the right-hand portion, right of the y-axis, the same as the area of the left-hand portion? Because it's symmetric, they're mirror images of each other. So why not do this? Why not just say double the definite integral from, say, 0 to infinity? Or you could do double from negative infinity to 0. Just get half of it and double it, and that will do it, all right? Okay, so there we go. That will get me the measurement that I need. All right, so okay. Now where are we at this point? Well, I've got that infinity, and that's not suitable for calculation. That does make this an improper integral. So as I've showed you before in other problems, I'm going to do limit b goes to infinity, and I'm going to replace this actual bound up there with a number b. Okay? All right, so that's what I will do. Otherwise, I got to work this same function. Find the antiderivative of that somehow. Now, I told you already, you might be really unhappy with this, but if that's true, you just let me know. I mean, I make the videos to suit your needs. I wasn't going to like spend a lot of time like working the integrals, because I kind of figured that that's behind us, and that we can rely more on some formulas, given that we paid our dues and we learned to do integrals by integration by parts and trig substitution and all that. So I wanted to tell you that the antiderivative of this one, if you did trig substitution, would be inverse tangent of 2x. Okay, so I'm just going to tell you that, but if you had gone back to when we learned trig substitution, that's the answer that you would have gotten. It would have been a fairly easy problem of that type. Okay, so let's see. I said just a second ago that it's inverse tangent of 2x. And we want to do 0 to b. All right. Okay, so let's put our bounds in, then evaluate our limit. So 2, limit b goes to infinity. All right. Tangent inverse 2b. Okay. Minus tangent inverse 0. All right, and I need that number to go to infinity. All right, that's what I need. That number right there needs to go to infinity. So, well, let's see. We have seen that already. You might not remember it, but we've seen that one. So, how does it work again? Let's see, okay, here it is. Here's the same sheet I used. I said, well, there's tangent of an angle is a number, or the angle is the inverse tangent of the number. Now, if that angle pushes to 90 degrees from below, the number goes to infinity. So if the number, if say inverse tangent of a number, if the number goes to infinity, that must mean the angle is going to 90 from below. Okay, that's the association. All right, so that's my preferred way to try to get you to see it. You might not like that way at all, so what's another way you can do it? Let's see, I want to make that number bigger and bigger. So b is going to infinity. 2b is also going to infinity. So what's tangent inverse of 100? 89 degrees. Let's go a little bigger. Tangent inverse of 1,000. 89.9 degrees. Yeah, you'll find that the bigger you make that number in there, and you calculate the inverse tangent, the closer your answer, your calculation will get to 90 degrees. That's the same thing as pi over 2. So I'm going to get 2, and then when I do that, when I calculate these, that limit, and then this number, I'll get pi over 2. Okay. So, and then tangent inverse of 0 happens to be 0. So this one, okay, well, that's just going to be pi. All right, so the total area under this curve, negative infinity to infinity, the whole thing, 3.14 square units, 3.14 units of area. It's about the same size. I mean, it really is amazing. This has infinite span to it. Nobody can hold this because it exists forever in each direction. But it's still about the same size as a 1x3 rectangle. It's amazing to me that that could happen. You might wonder, one more parting thought. How can it, like, if this really is infinite span, like, if nobody can hold this shape because it keeps going forever, there's this tiny sliver of space in both directions, how could it have a finite area to it? How can this be about the same size as a 1x3 rectangle? Well, this little space is always there, but it diminishes and shrinks so fast and gets so incredibly small as you go outward that it turns out to not be significant. All right, that's how a space, a region like this, can have a finite area to it. So I'll say two things. One, that about integrals like this, we say they converge. Two, I'm going to say that that region that was pictured up at the top of the page has a finite area to it. All right, it's not really infinite in its size.